Imagine this. You've been climbing a mountain for hours. Your legs are dead, your soul is gone. You finally reach the top. You scream, "I did it." And then someone points behind you and says, "That's not the mountain. That's just a bump. Congratulations. You just experienced a local minimum." In machine learning, we train models by minimizing something called loss. Think of loss like error. The lower it is, the better your model. So we imagine this giant landscape with hills and valleys. And our job? Drop a ball and let it roll to the lowest point. Simple, right? Yeah, except the ball has commitment issues. Here's the problem. This landscape is not smooth. It's messy, chaotic, full of traps. Your model rolls down, finds a small dip, and goes, "Yep, this looks like success." But it's not the lowest point, it's just the first comfortable one. That small dip, that's your local minimum. The deepest valley, that's the global minimum. The deepest valley, one is good enough. The other is actually optimal. And your model can't tell the difference. Now here's where things get interesting. In academia, this is fine. Mathematicians be like, "Ah yes, convergence to a local minimum. Fascinating. Publish the paper." Because theoretically, you did minimize something. But in industry, this is not fine. Because your model is not solving a math problem. It's making decisions. Real decisions. With real consequences. Let's say you build a fraud detection system. Your model looks great. 92% accuracy. Boss is happy. But the model is stuck in a local minimum, which means it's missing important fraud patterns. Or take recommendation systems. You watch one video and suddenly your entire feed becomes trash. That's a model stuck in a bad optimum. Now imagine this in self-driving cars. The model isn't terrible, just slightly wrong. And in the real world, slightly wrong is dangerous. Here's the scariest part. Local minima don't look bad. They look stable. Loss is low. Metrics look decent. Dashboards say all good, but underneath, your model is underperforming. Quietly, consistently. And escaping a local minimum is not easy. Because once you're inside, everything points inward. Gradients say stay here. Loss says you're doing great. Your model literally has no idea that something better exists. So what does industry do? It cheats. We add randomness, so the model can jump out. We add momentum, so it doesn't stop too early. We use smarter optimizers like Adam, because plain gradient descent is too naive. Because in the real world, optimization is not just about finding a solution. It's about not getting stuck in the wrong one. And that's why industry hates local minima. Not because they're wrong, but because they're convincingly wrong. Now you might be thinking, okay, cool concept. But this is basic stuff, right? Old machine learning problems. Wrong. This problem is very much alive today. In fact, even modern AI systems, including large language models, struggle with this. Many models today are heavily optimized for benchmarks. They perform incredibly well on tests they've effectively learned. But that doesn't mean they truly understand. In a way, they've found a local minimum in performance. Good enough to impress, but not deep enough to generalize. And that's one of the reasons why models hallucinate. Because they're confident inside a region that looks optimal, but isn't globally correct. They've learned patterns, not truth. Now, of course, hallucinations are not only caused by local minima. There are many factors: training data, objective functions, architecture, but the idea remains the same. Optimization doesn't guarantee truth. And that's the real lesson. Just because an AI system looks confident doesn't mean it has reached the right answer. It might just be comfortably stuck. If you want to understand what's really happening inside AI, not just the hype but the truth, subscribe to Hidden Gradient, Math through AI Reality.